Today, it will be last lecture on optical fibers. Yes, we have covered almost everything, whatever is there in your syllabus. And from next time, we'll start with a new unit, that is electrodynamics. And for electrodynamics, some basics of earlier classes are required, and I hope those basics you know. It is about electricity and magnetism. So you know, you have done electricity as well as magnetism in your lower classes and in quite detail. Then basics of mathematics, differential calculus is also required, and that I hope you have done in mathematics this year. Have you done it? It is like uh, differential operator, del operator, divergence of a vector field, gradient of a vector field, curl of a vector field, or gradient of a scalar field, curl of a vector field. Have you done these topics in mathematics?
No, sir.
No, sir.
No. Okay, so then my first lecture will be on some basics of mathematics which are required to do or to start with this chapter. Okay, so tomorrow we'll or let us see अगर आज हमें time मिल जाता because very small portion of this is left. So if I can finish this before 11, we'll start with those basics as well. I hope my screen is visible to all of you, and more than 60 students have joined, so we can start with today's lecture. Screen is visible to all of you.
No, sir.
No, sir.
No, sir.
I have not shared my screen.
No, sir.
No, sir.
Okay, let me share it again. Is it now visible?
Yes, sir.
Yes, sir.
Yes,
Oh,
sir.
okay. Today we'll be discussing about losses. Who is this? किसी का mic unmute है?
Sahil.
Mute your mic. Because when I open my PPT, I cannot see Google Classroom screen.
कर लिया सर म्यूट कर लिया
Okay. So today's topic is losses in optical fiber. It is attenuation of light which we send through the optical fiber. Before starting with this, let me give you a review of what we have done till now. We discussed structure of optical fiber. We have done basics, even basics, or those basics are very much clear to you. बीच में mic is some कुछ है ना, अभी भी कुछ mic किसी का unmute हो गया है. Okay. So we started this chapter with structure of this optical fiber, and you know structure is very important. We said that it is very small in size, diameter is in micrometer range. Most important part of structure is what it is, core cladding interface. Because we know what is importance of core cladding interface. Light propagates due to that total internal reflection which happens at core cladding interface. The propagation of light through the optical fiber is at the core cladding interface, and even losses, some losses, they are there due to this core cladding interface. So losses as well as propagation, both they take place at core cladding interface, or they are due to this combination of core cladding interface. Rest, you know that principle is total internal reflection through multiple reflections, total internal reflections at the core cladding interface, light propagates through the optical fiber. Launching of light is also important. It is not only propagation of light. Propagation is, it depends on the combination of core cladding refractive indices. But how we launch light from outside, that we discussed, we said that acceptance angle plays role here. It is not that every ray which we try to launch through the optical fiber that propagates through the optical fiber. It is all about only those rays which undergo total internal reflection at the core cladding interface. So for that we decided, or for that we discussed what we mean by acceptance angle. So whenever light is made incident at this acceptance angle or less than this acceptance angle, or launched at this acceptance angle or less than this acceptance angle, propagates through the optical fiber. And we related this because acceptance angle depends on what? It depends on total internal reflection, condition of total internal reflection. If it happens, then we know that the angle is less than the acceptance angle. And then we related it with numerical aperture. We said that the refractive indices, they decide what will be the condition for total internal reflection, which in turn decides what should be the angle of acceptance for the given optical fiber. So we wrote that expression. I'm not writing because we have done all this. I'm just giving you a review what we have done till now. So we said that numerical aperture, we can write numerical aperture as in terms of n1 and n2. It is under root n1 square minus n2 square. N1 and N2 are very much clear to you now. Conventionally, we are using N1 for core, refractive index of core, and N2 for refractive index of cladding. And we also know this, that N1 is always less than N2, and in no condition N2 is greater than N1, because then we cannot expect total internal reflection and we cannot propagate our signal through the optical fiber. And then we discussed more parameters like fractional refractive index change. We can write a numerical aperture by doing small mathematics in terms of this delta, fractional refractive index change as well. So important is acceptance angle and cone of acceptance. Then we also discussed different optical fibers, types of optical fibers. It depends on path of the ray through the optical fiber, and it also depends on the combination of refractive indices or refractive indices of core cladding interface or core and cladding. On if we decide or we categorize optical fiber on the basis of path, then we say that if there is only one allowed path through a given optical fiber, and that is along the axis of the optical fiber. So if ray propagates along this path, only allowed path, then it is single mode fiber. And if there are number of allowed paths making different angles with the axis of the optical fiber, one is along the axis, another is making some small angle with the axis, and then it increases up to the critical. We know that total internal reflection. Uske baad no light can propagate. So this is what this is. These are different modes. These are different paths along which light can be propagated through the optical fiber, and this this type of optical fiber is called multi-mode optical fiber. Then, as I said, on the basis of index or refractive index of the core, mainly core through which light propagates. Core is to propagate light and cladding is to confine light within the core. Okay, so graded index and step index fiber, we categorized, we said that optical fibers, they fall under these two categories. Step index fiber is when we say that the refractive index of the core is uniform throughout. There is no change in refractive index of the core. It changes only at the interface. So that is step where there is change in the refractive index. So path of the light rays in such type of optical fiber is a straight line path, because there is no change in light travels within the core, and within the core there is no change in refractive index, so it moves along straight lines between successive collisions or between successive total internal reflections. Then we have graded index, where we said that core is refractive index of core is not constant or uniform throughout, but it changes, and at the center of the core refractive index is maximum, and it goes on decreasing as we move towards the cladding from the center of the core. Okay, so we have done everything in detail, so I'm not. And one more important thing, most important thing which we discussed, that is dispersion in optical fiber. And the reason for dispersion, we gave two reasons for dispersion. One is due to different modes, different paths light travels through the optical fiber. The shortest path is the path along the axis of the optical fiber, and the longest path is the path, or the path which makes angle theta c equals to cos inverse of n2 over n1 with the axis of the optical fiber. So due to this difference in time taken by different modes to travel along the optical fiber, we see this dispersion, which is called intermodal dispersion due to different modes. Then there is one more type of dispersion, material dispersion, or you say intramodal dispersion, which is due to what? Which is due to different wavelengths travel with different speeds along the same mode due to refractive index of the optical fiber, and that also leads to dispersion of the optical fiber in optical fiber. And dispersion, why it is important? Because it decides what should be the length of the optical fiber for given we want to send some signal, or we say that it is 10 megabits per second. Okay, as we discussed on that day. So it is what it is. We are sending pulse, and that gets broadened when it comes out of the optical fiber. And why it gets broadened? It gets broadened due to this dispersion, due to difference in time taken by different modes to travel along the optical fiber. So this is what we have done till now.
सर
Yes, beta.
सर आप कुछ लिख रहे हो ना?
ना अभी मैं कुछ नहीं लिख रहा हूँ, बस अभी रिव्यू, दिस इज व्हाट वी हैव डन टिल नाउ, अभी तक जो हमने, जस्ट टू मेक कंटिन्यूटी, है ना. तो नाउ
उनके सर डाउट आ रहा था सर कुछ लिखने के, इसलिए.
नहीं, नाउ आई विल बी राइटिंग, ओके. So now next topic of optical fiber is attenuation. It is what it is, loss of signal. Dispersion हमने किया कि different time लेगा अगर ray, fastest ray and the slowest ray, and there will be delta t. There will be spreading of the signal, or spreading of the pulse which we are sending through the optical fiber. Now we are talking about attenuation in optical fiber. Attenuation in optical fiber is like what? If you remember, we discussed it in case of laser as well. Laser mein, we were saying we were interested in amplifying our signal, and I said that I have some material medium. These are the atoms, molecules of this material medium, and if we make light incident on this material medium, here light propagation is what it is through material medium, and this is not guided propagation. But here, in case of optical fiber, we have guided propagation of light. We have optical fiber. So this is the only difference. Rest is what we said, that whenever we make light incident on this material medium, this light, it gets absorbed by the material medium, and it is also scattered by the material medium. And what we get in the output is, it is attenuated light. It is what it is, light signal whose amplitude is or intensity is very low. This attenuation, this loss in intensity of the signal is due to two reasons here. We have given two reasons. One is due to absorption of light, and another is due to scattering. And then we wrote one expression. We said that if intensity of the incident light is I naught, and intensity of the light here is what it is. Let me say I out in which we are, and I in. Then we say that this which intensity which we are getting in the output is less than what is in the input. So it decays exponentially, and it is e raised to the power minus attenuation coefficient times distance traveled by the light through the given material medium. And here we have two reasons, that is absorption and scattering for loss of signal or for the loss of intensity of the light. So it depends on these coefficients, that is coefficient of absorption plus coefficient of scattering. Okay, so we say that this is how, let us discuss it in case of optical fiber. I say that this is my optical fiber. I'm launching light. I have some, you can say, source of light here, and I'm sending light pulses through this optical fiber. And here we have photo detector, which is detecting this light detector. And if there is loss in power which we are sending in is this, and detected by the detector power is P naught. So what happens that P naught is what it is less than Pi, and this is also due to what it is due to absorption of this light by the material, by there will be reasons, impurities present in this, by defects in the structure of the fiber, etc., or due to some other reasons. So what we get in the output is not equal to this. In case of ideal case, if we say it is ideal fiber, then we can say that whatever is sent in, whatever is the power of signal we are sending, same power we are getting in the output. And this is ideal case, which is not seen, so which is not possible. And this is also exponential. These are also exponentially related. We can say that this power in the output is power in the input. It decays exponentially, and it is that attenuation constant times length of the optical fiber. This is length of the, or you can denote it by L. So this is L is the length of the optical fiber here. So distance traveled by the light through the optical fiber is L, and this is attenuation coefficient, and it is having both the components, that is scattering as well as absorption of light. Okay, and this coefficient alpha is in units kilometer per kilometer. And we can write that this is P naught divided by Pi this is the fraction of the power which we get in the output. To get rid of this exponential term here, I take log on both sides. So I can, this is P naught divided log of this is equals to minus alpha L, and then we can write attenuation coefficient. It is equals to 1 over L log P I over P naught. Minus sign is absorbed and it is written as Pi over P naught. Or we can convert, or we can write this as to the base 10, it is log this divided by this. So this is what this is attenuation coefficient. Okay, in ideal case, when we say that Pi is equal to P naught, Pi is equal to P naught, then this will be 1 and log of 1 is 0 and attenuation is what it is, 0 in that case. Attenuation coefficient is 0. There is no attenuation. This will be 0 and you can say that P naught is equal to Pi. तो आइडियल फाइबर्स नहीं है, कोई भी फाइबर्स आइडियल नहीं है. हर एक फाइबर में देयर इज लॉस, देयर इज एटोनेशन, and this attenuation we'll be going into details why this attenuation is there, what are the reasons for attenuation of light or for the loss of the signal. So there are two categories of attenuation. First is intrinsic attenuation and other is extrinsic attenuation.
हेलो सर, आपकी आवाज़ नहीं आ रही.
सर चले क्या? चले गए क्या?
हाँ चले गए.
आ जाएंगे.
शायद नेटवर्क इशू होगा सर का कुछ.
Yes, sir.
Yes sir.
Okay.
Yes, sir.
Who is singing? Who is singing? Saroj. रोल नंबर 26. हाँ जी, म्यूट कर लीजिए बेटा. हाँ, अब मुझे ये बताइए, मेरा सिग्नल कब गया था? व्हाट वी वर डिस्कसिंग?
वो इंटेंसिक और इंटेंसिक वाले के सर.
वी वर डूइंग
इंटेंसिक एंड एक्सटेंसिक सर.
okay, let me share my screen. Absorption losses we discussed. Absorption, we discussed absorption losses or not?
No sir.
Okay. So I said only this. शायद यहाँ तक हम क्या, मैंने सिर्फ आपको ये बताया कि जो लॉसेज हैं वो दो तरह के हैं। एटोनेशंस जो हैं दो कैटेगरीज में हम उनको डिवाइड करते हैं, इंट्रिंसिक एटोनेशन एंड एक्सट्रिंसिक एटोनेशन, है ना। तो हमने कहा कि जो मटेरियल की वजह से लॉस है दैट इज इंट्रिंसिक लॉस, whereas extrinsic loss is due to external reasons, due to external forces such as bending and other environmental type of forces. Okay, so first is intrinsic attenuation, intrinsic loss. It is due to, as I said, it is due to, this is inherent property of the material, or it is inherent in material that उसमें कुछ impurities हैं, impurities in the glass, और जब मैन्युफैक्चर करते हैं हम, we cannot eliminate all the impurities, some impurities they remain there, और इन impurities की वजह से जब भी सिग्नल हिट करेगा इन impurities in the fiber, either light is absorbed by these impurities or it is scattered by these impurities. Okay, so that is reason for intrinsic attenuation. And we further divide this intrinsic attenuation into two categories. We say that it is material absorption or it is Rayleigh scattering absorption. Okay, material absorption means what? When we have impurities such as hydroxyl ion, means OH negative molecule. ठीक है, while manufacturing, जब हम मैन्युफैक्चर करते हैं फाइबर को, तो कुछ मॉइस्चर की वजह से इस तरह के रेडिकल्स दे रिमेन इन द ऑप्टिकल फाइबर, एंड देयर आर सम अदर impurities present in the optical fiber. For example, transition metals, copper, nickel, chromium, vanadium, magnesium, these are the impurities in the optical fiber. बहुत कम अमाउंट में by refining or by making manufacturing process better and better, we can reduce these impurities, but we cannot reduce them to zero. Some impurities and the सबसे ज्यादा जो impurity रह जाता है और सबसे ज्यादा जिसकी वजह से लॉस होता है, that impurity is OH ion. So moisture वाला जो content part है, that and it cannot be reduced. This leads to maximum absorption. So 3 to 5%. If we compare it with the Rayleigh scattering, so material absorption total loss का, it is only 3 to 5% of the total loss. So contribution of material loss or due to material absorption loss, that is not that much. And this is whenever light is made incident or it propagates through the optical fiber due to presence of these impurities, OH negative ions and other impurities, light is absorbed by these impurities and ये vibrational energy states जो हैं उनकी excite हो जाती हैं in impurities. Okay, so in that region we get what? We get loss. जब भी हमारा जो light की energy होगी, that matches with the vibrational energy states or electronic energy states. ठीक है, so जब UV wavelength का light आप भेजोगे तो electronic energy states excite होंगे इनके, and if we send IR wavelength, then their vibrational, that matches with the vibrational states of these impurities. So we see what we see, absorption of light due to presence of these impurities. Then we have Rayleigh scattering. Another is what it is, Rayleigh scattering. And Rayleigh scattering, it contributes maximum in attenuation. More or 96% of the total loss is due to Rayleigh scattering. Loss of light is due to Rayleigh scattering. And how this happens, why it is there is this scattering? It is due to when we manufacture our fiber. While manufacturing, there is local microscopic density variation in some small region. You can say in this small region, while manufacturing, we are trying to manufacture what that core refractive index should remain same throughout, but there is small variation in the refractive index in this local region. There is small variation in the refractive index here as well as in some other regions. That's 2 पे sir. So due to this, there is variation of refractive index. Density is different, so there is a variation in refractive index, and these regions, they act as obstacles or obstructions for light, and light gets scattered in all directions due to presence of such local regions in the optical fiber. And Rayleigh scattering जो है वो that is inversely proportional to fourth power of wavelength. Means lower wavelengths, they show more Rayleigh scattering. So that means it sets lower limit for on the wavelength that can be transmitted by a glass fiber, है ना? And it is 0.8 माइक्रोमीटर के नीचे की जो वेवलेंथ होंगी वहां पे बहुत ज्यादा Rayleigh scattering होगा. So this is the limit which we can send. So any wavelength below 800 or 800 nanometer, if I convert this into nanometer, is unstable for optical fiber because attenuation is too high. Rayleigh scattering attenuation is too high. Okay, और absorption जो है वो किस रेंज में absorption ज्यादा होता है? When 1700 nanometer, 1700 nanometer is not possible क्योंकि उस केस में infrared absorption maximum हो जाएगा and light cannot be propagated through the optical fiber. So this is we have discussed all this. Scattering we have discussed. Then we have radiative losses. This is extrinsic losses. These losses are due to what? These are due to bending of optical fiber. Macro band means big band, and micro, दो तरह के bends हैं. So if we have macro bend, which is visible, large scale bend which is visible. So at the fiber bend, जहाँ पे bend है fiber का, it is like this. We have optical fiber, and there is a sharp bend here. You can say this is the sharp bend in the optical fiber. This bend is what it is, sharp bend. So at this, there is what the strain is produced. We have this fiber. If we bend it, so strain is produced here, and due to this strain, it affects the refractive index and the critical angle. Okay, यहाँ पे total internal reflection हो रहा है, but due to strain here there is change in refractive index, and और उसकी वजह से जो total internal reflection condition था वो fulfill नहीं हो रहा है at the bend due to strain and due to change in refractive index. Then other type of bends are what? They are not macro bends, but they are micro bends. यहाँ पे kink, यहाँ pressure की वजह से, force की वजह से there are small kinks, small bends in the optical, small scale distortion, localized है, जो pressure की वजह से आ रहा है. ठीक है, might be due to temperature, tensile stress है, और कोई crushing है, force है, उसकी वजह से micro bends आ गए. Imperfection or cylindrical geometry में there is imperfection in this cylindrical geometry. It should be very perfect geometry, this cylindrical geometry, but it is what it is, some bend here, a very small bends due to some pressure here, due to force, due to temperature. So these micro bends, they are also responsible for attenuation, because light, when it strikes these small bends, or it gets scattered. Total internal reflection is not fulfilled, it gets scattered, and due to this it leaks out of the optical fiber. So these are some losses in optical fiber. Now let us discuss one more thing, that is how we make sensors from using these optical fibers. How we make sensing device from these optical fibers. If you have any idea, can you say for what purpose we can, or for what sensing we can use these optical fibers? Basically, it is what it is. Whenever there is change in property, that property change can be sensed by, it is what it is, basic structure of the sensor is what it is. Let me create one slide here so that you can. Okay. Uh, basic structure of sensor is what we have. Light source here, and then we have optical fiber. Light is transmitted through the optical fiber and it is detected here. We have photo detector here. So when light travels through this optical fiber, वो losses को छोड़ देते हैं, but due to some other reason, if there is what there is change in the signal that is detected by the detector. That will sense what this change in the intensity of the signal is detected by the detector, and then it can sense that something is there, change is there in this part of the detector, which is detected. So this is how it works. It is light source, it is optical fiber, and then we have photo detector. Okay, we have three different type of sensors. Main sensors. One is temperature sensor. It can sense change in temperature. We have it made of based on optical fiber. We can make temperature sensor, and this temperature sensor will even sense change in temperature of 0.001 degree centigrade. This is the accuracy of this sensor or sensitivity of the sensor which we make out of optical fiber. How we make this sensor? This is based on when temperature is measured by the, or you can say, let me draw it for you. This is what this is. This is based on we have a material which is, this is silicon material, and what property of this silicon material we are using here, that it absorbs, or capacity of absorption of light by this silicon varies with temperature. So it can absorb different amount of light at different temperatures, and this is what we'll be using. So let us use this material silicon, and we send light up to this silicon through this fiber. Okay, and light reflected from this silicon after absorption it travels through this fiber. So we have two branches of fiber. This is one of the branch, and this is what this is branches, and this is the second branch of it. So we have here source of light. This is my source. I produce light. It travels through this optical fiber, and it goes up to silicon. And this light at different temperatures, different amount of light is absorbed by the silicon. And here we have what we have placed, a reflecting mirror, highly reflecting mirror. So whatever it goes through the silicon, that is reflected back again. So two times light travels through this silicon. And if there is no change in temperature of this silicon, so intensity of light detected by the detector will be same every time. But if there is slight change in the temperature, it is even this much, then that is then this will absorb different amount. It is what silicon, it absorbs different amount of light at different temperatures, and due to this change in temperature, it will absorb more or less light, whatever. and that change in intensity of light is detected by the detector, and this is how this works. So there is modulation in the signal which is detected by the detector, and this modulation happens due to absorption of light at the silicon, or different amount of light absorbed at different temperatures at the silicon. So multi-mode fiber is used for this detector, and as I said, that accuracy is very high, and even it can be used to not to just detect this temperature change, and we can calibrate it to even measure this temperature, or any temperature. So this is what this is based on optical fiber. This is temperature sensor. Then we have another type of sensor. It is displacement sensor or motion sensor, which can detect motion of any object, or it can detect displacement of any object. It is again based on optical fiber. In this detector, in this sensor, we use pair of two optical fibers, adjacent optical fibers. One is to carry light from source to the object whose displacement we want to measure, or whose motion we want to measure, and other optical fiber is to carry light back to the photodetector. The basic structure is always what it is: source, optical fiber, and then detector. So here also we have what we have. We have source of light which carries signal up to the object whose displacement is to be measured. And then there is another optical fiber which carries signal back to the photodetector, where by the photodetector, and then it senses displacement. So let us see what it is, what is the construction of this. This is the object whose displacement we want to sense, and we have two adjacent optical fibers. This is one of the fibers, okay, and I have one more fiber. This is placed positions adjacent to each other, or they are very close. Let me chalo, theek hai, it is like this. So this is the arrangement. So light travels through this. Initially, let us say that there is no separation between the object and the optical fibers. So distance between the object whose displacement or whose motion we want to sense from the optical fiber is zero. There is no separation here. So whatever signal will come, that will be reflected back, and that will go through the same fiber, and nothing will go through this fiber. This is source of light, and here we have photodetector. We are detecting light here. So nothing is detected by light. Nothing is detected by detector till separation between the object and the sensor is what it is, or and the optical fiber is zero. But if we increase distance, okay, if we move this arrangement away from the object whose motion we want to sense, so with this increase in distance, you can say that we have increased this distance. Now light which will reflect back, that also some part of that will also travel through this the other optical fiber, which will carry it to the detector. Okay, and we further, if we increase, or when this gap is increased, gap between the object and the optical fiber, it increases more. Some light is captured by the receiving fiber, and एक ऐसा distance आएगा, a distance will be reached at which a maximum reflected light is received by the detector. Further, if we increase, उससे भी ज़्यादा अगर increase करें distance, then there will be further decrease in intensity of the light received. Okay, initially when we increase distance, so intensity will increase here, intensity detected by the detector will increase, maximum will be reached, maximum when maximum light is detected by the detector. Further increase in the separation will decrease the intensity of the light received by the photodetector. And by proper calibration, we make calibration. Okay, so we can obtain displacement of object in terms of strength of the output signal of the photodetector. Okay, and then we have third type of sensor. This is motion sensor. Then we have liquid level sensor. And sensor or detector. What this is, in this we have again, this is my source of light. I have detector here which will detect light, and in between these two I have optical fiber which is specially designed. This is the shape of that optical fiber, and this is the level of liquid or the container vessel in which we have liquid. So light is sent through this or sent from source, okay, and it is reflected here at 45 degree or 90 degree. Then it goes to this, it is total internal reflection, and when we see what light is detected back by the detector. So at air, you can say this is air core interface. We see that there is total internal reflection is there. But if level of liquid, it rises in the vessel and it goes to this level, then you can see that now interface is not core air interface, it is core liquid interface. And this liquid should have this refractive index of this liquid should be more than the refractive index of your optical fiber. Okay, so total internal reflection possible nahi hoga because we have what we have liquid of more refractive index, and light will leak out of the optical fiber. Now, nothing will be detected by the detector, nothing will reach at the detector, and there will be zero intensity is received by the photodetector, and it can sense that level जो है water का वो increase कर गया कुछ. So this is all about optical fiber. Okay, तो इसके बाद अगर अभी टाइम है तो we can discuss. It is 5. Chaliye. We have 2 minutes time, so we'll do it tomorrow only. If you have anything, because we have discussed structure of what is important in this unit is it is structure of optical fiber,